Hey guys, so today we're going to go over background 7, induction. So first we need to cover alternating currents. So direct current flows in one direction. Alternating current is a current that periodically changes direction. That's all the difference is. It just changes direction periodically. So wave properties, peak to peak of a wave is the distance from the lowest peak to the highest peak. The period of a wave is the amount of time in seconds required for the wave to complete one full oscillation. The frequency of a wave is the number of oscillations of the wave per second. The units of this is hertz, and it can be found by 1 over the period. And then the angular frequency of a wave is 2 pi times the frequency. Now we're going to go over an example of a sine wave. So here is a sine wave. You can see the peak to peak of this wave is 2 because the lowest peak is -1 and the highest peak is 1. So the difference between those is 2. So the peak to peak is 2. The period is 2 because every 2 seconds it completes one oscillation. The frequency is 1 over the period. So 1 over 2 gives 0.5 hertz. And then the angular frequency is 2 pi times the frequency, which gives pi radians per second. Here we have a square wave. The peak to peak is 1 volt. You can see that because the lowest point is 0 and the highest point is 1, so it's 1 volt. The period is 3 seconds because it takes 3 seconds to do a full oscillation. So an oscillation includes the up and the down, and so one whole oscillation happens over 3 seconds. And that means the frequency is 1 over 3 seconds, because frequency is 1 over a period, which is 1 over 3 seconds. 0.33 hertz. And then the angular frequency is 2 pi times the frequency, which is 2 over 3 pi radians per second. Then for this one, the peak to peak voltage is 2 because the lowest peak is 0 and the highest peak is 2. The period is 1 second because it does a complete oscillation all the way up and all the way down in 1 second. So the period is 1 second. The frequency is 1 over the period, which is 1 hertz. And then the angular frequency is 2 pi. F equals 2 pi radians per second. So these are pretty straightforward. These are just 3 important types of graphs that you need to know: triangle waves, square waves, and sine waves. Okay, so now we're on magnetic flux. Magnetic flux is the amount of magnetic field that passes through a surface. For a coil, the magnetic flux through the coil is equal to the magnetic field passing through the coil multiplied by the area of the coil times the cosine of the angle between the field and the face of the coil. So that's a lot of words. If we have a coil of area is 2 meters squared, and we have magnetic field passing through the coil of B equals 1 Tesla, then the magnetic flux would be area times the magnetic field, which would give you 2 Tesla meters squared. If the magnetic field was not perpendicular to the area of the coil, right, if it was coming in at an angle, an area of 3 meters squared, and then this magnetic field is of 2 Teslas, and then this angle right here is 30 degrees. Make sure you use the angle that is perpendicular to the face of the coil and the magnetic field. So then we have the flux is A B cosine of theta, which is 3 times 2 times cosine 30, which is 3 root 3 Tesla meters squared. So magnetic flux is really a measure of how much magnetic field passes through a coil. Okay, now we're on Faraday's law. This is where the interesting stuff starts. So Faraday's law states that a changing magnetic flux through a coil will induce an EMF within the coil. That's a lot of big words, but to shorten it, if you change the magnetic flux, it causes a current. So here we have a coil and we have a magnetic field passing through. If the graph of the magnetic field over time is constant, then the EMF over time is 0. And the current through the coil over time is also 0. If the magnetic field is changing through the coil, then it will induce an EMF within the coil, and that EMF will cause a current within the coil. So here, if the magnetic field is changing, then the EMF will be also changing. And the current through the coil is proportional to the voltage through the coil. So this change in magnetic flux is what causes the EMF. Here we have a decrease in magnetic flux, so we have a negative EMF. That's all that Faraday's law states, and here is the equation that relates the magnitude of these graphs. So now we're going to put this equation into practice. So imagine we have a coil with 4 turns, and then the magnetic field changes through the coil with a frequency of 5 Hertz, and the magnetic field is a triangle wave, and the minimum magnetic field is -2 Teslas, and the maximum magnetic field is 2 Teslas. The reason one's negative and one's positive is because initially the magnetic field is in one direction, then the magnetic field changes direction to be 2 Teslas in the opposite direction. And so one is negative and one is positive. The area of the coil is 3 meters squared. We wish to find the induced EMF within the coil. To do this, we will have to use this equation. Induced EMF is NA times delta B over delta T. So we have the number of turns and we have the area, right? Number of turns is 4, area is 3. But we are missing the change in magnetic field over the change in time. And this is the hardest part right here. So we have this delta B over delta T. So what we're going to do is draw a graph of the magnetic field versus time. So we know since it's a triangle wave with frequency of 5 Hertz, then the period of the wave is 1 over frequency equals 0.2 seconds. That means one oscillation happens every 0.2 seconds. And we know the minimum magnetic field is 2 Teslas, and the maximum magnetic field is 2 Teslas, or -2 and 2. And if here we have 0 seconds, then here we have 0.2 seconds. And that means up here we have 0.1 seconds. Using this, we can find that during the changing magnetic field from here to here, and from here to here, and so on from here to here, all of these slopes, the change in magnetic field over change in time, will be 4 Teslas, because it goes from -2 to 2, and that happens in 0.1 seconds, meaning 40 Teslas per second is our delta B over delta T. And then this comes out to 360 volts. And notice that when the magnetic field is increasing, then that EMF is positive because the slope is positive. When the magnetic field is decreasing, then the EMF is negative because the slope is negative. So this is what the graph of the EMF would look like. The EMF would come out as a square wave, even though the magnetic field was a triangle wave. Now we're going to use these equations to solve a much harder question. So first, let's imagine we have an alternating current traveling through a large coil over here, big coil. And then we have a smaller coil being held at the center of the larger coil. The alternating current traveling through the big coil generates an alternating magnetic field within the big coil. We'll say that the alternating current is a triangle wave, and the peak to peak of this current is 4 amps. And then the number of turns for the big coil is 3 turns. The radius of the big coil is 2 meters. The frequency of the alternating current is 2 Hertz. We also know that the number of turns for the smaller coil is 5 turns, and the radius of the smaller coil is 1 meter. Our goal is to find the EMF induced within the small coil. Now, how do we do this? First, we can use an equation from last week. So we know the magnetic field within a coil due to the current is given by the following equation. So the magnetic field within the big coil is given by this. That means the magnetic field within the small coil is given by this equation. We can use this to find the induced EMF within the small coil using this equation. Now we're left at delta I over delta t. We want to know the change in current over the change in time. This, again, we're going to have to draw a graph of the current versus time. So I will do that now. We know that the peak-to-peak current is 4 amps and that it is a triangular alternating current. We also know that the frequency is 2 hertz. This means I can label this bottom current at -2 amps and this top current at 2 amps. Since the frequency is 2 hertz, then we have 2 waves per second. And the period is 1 over frequency, which gives 0.5 seconds. Therefore, we know that each of these waves happens in 0.5 seconds. That means that one rise or one fall happens in 0.25 seconds. We can then use this for our delta I over delta t. We know that the current rises a total of 4 amps over a period of 0.25 seconds. This gives us a delta I over delta t of 16 amps per second. We can use this and plug it back into our old equation. And this gives us the theoretical induced EMF within the small coil. The induced EMF will look like the following graph. We know that the EMF has its peak value and minimum value while the magnetic field is changing. Because the slope is constant, then the EMF is constant for that period. When the delta I over delta t is constant, then we have a constant EMF. Constant delta I over delta t gives us a constant EMF. This is very important to understand. It is a changing magnetic field through the small coil that induces a current. It is not the magnetic field. It is the change in magnetic field that induces a current, that induces an EMF within the coil. If the magnetic field is constant, then no EMF is induced. Now we're going to talk about Lenz's law. Lenz's law gives us the direction of the induced EMF within a coil when we change the magnetic field through a coil. Lenz's law relies on one principle, which is the principle of conservation of energy. Here I will give a short proof of Lenz's law, which is also an explanation of how it works. Suppose we have a coil with initially a magnetic field directed down through the coil. Let's say we decrease the strength of this magnetic field. So after a few seconds, our magnetic field is smaller. This means our change in magnetic field was upward through the coil. Now, this change in magnetic field will induce an EMF. The EMF will cause a current. The new caused current will create a magnetic field. This will again change the magnetic field. So let's first suppose that this induces an EMF causing a current in this direction. If we do this, then this new current induces a new magnetic field that is up through this coil, using the right-hand rule that we learned from last lab. The induced magnetic field will be up if the current is in that direction. If the induced magnetic field is upward, then the change was upward. This will increase the current further, which will induce a larger magnetic field, which will increase the current further, which will induce a larger magnetic field, which will increase the current further, which will induce a larger magnetic field. And this will continue forever. This violates the conservation of energy. If we do this, we would get infinite magnetic field off of a small current. Small change in magnetic field leads to an infinite magnetic field. Therefore, we know if the change in magnetic field was up through the coil, then the induced current must be in the opposite direction. This means that the induced magnetic field will be down through the coil. This induced magnetic field is against the direction of the original change in magnetic field, which does not cause an infinite chain reaction. Therefore, we know if we ever have a change in magnetic field, the induced magnetic field opposes that change. The induced magnetic field opposes the change in magnetic field. From the direction of the induced magnetic field, we can determine the direction of the induced current. Let's do an example. If we have a coil with original magnetic field into the page, then the strength of the magnetic field is increased. This means that the change in magnetic field is also into the page. This means that the induced magnetic field must be opposite of the change in magnetic field. So the induced magnetic field must be out of the page. If the induced magnetic field was out of the page, then the induced current must have been in this direction. If you don't understand how I got that direction of the current, you must look at lab 6. I'll do one more example. Suppose we have a magnetic field into the page. The strength of the magnetic field decreases. That means the change in magnetic field is out of the page. If the change of magnetic field is out of the page, the induced magnetic field must oppose this. So the induced magnetic field is into the page. Because the induced magnetic field is into the page, then the induced current must be clockwise. Again, if you don't understand going from B induced to the current induced, then you must review lab 6. That is everything for this lab.